In the previous classes, we discussed about the resistivity. So for a particular material, the resistivity remains as a constant. So we know if you take copper, we have a particular resistivity, and if you have any other alloy or a semiconductor, we have a resistivity. So in the equation, when we are calculating the resistance, there R is equal to rho L by A, where there we took the resistivity as a constant. But we know the resistivity is not strictly a constant. When the other conditions changes, the resistivity also will change. The most important thing is the temperature. The resistivity is due to the movement of the electrons. When the electrons are moving, it will undergo collisions. So between two collisions, there is some time interval. That time interval we will mark as tau. Now what happens is when temperature changes, these collisions also will change. That is, the more and more electrons will become free, so that the number of collisions also can increase. So how it is varying, how the resistivity varies for any material according to the temperature, that is determined by a particular property of the material, that is called as the temperature coefficient of resistivity. So this temperature coefficient of resistivity, that is a small positive value for our metals, and it is negative for semiconductors. The meaning is, in the case of our metals, when the temperature increases, the resistance also increases. In the case of semiconductors, when the temperature increases, the resistance reduces. So first we will go for the equation of resistivity, the relation between the temperature and the resistivity. And afterwards, we will draw the graph for a conductor like copper and an alloy, and again for a semiconductor. So how it varies. So why it is happening like that. Based on the equations also, we can discuss what is happening here. So temperature coefficient of resistivity, we will write it as alpha. That is very, very important here. Now we will go to the equation of temperature coefficient of, equation for the resistivity of a material at a particular temperature T. In order to get this resistivity, we should know the resistivity of this material at another temperature, a non-temperature. For example, if you know what is the resistivity of a material at 20 degree, and then you can calculate for 100 degree. There you should know the temperature coefficient also. So we will go to the equation and we will continue. Okay, so the resistivity of a material at a temperature T is given by the equation rho T is equal to rho 0 into 1 plus alpha into T minus T0. This is the equation. This equation is very, very important. So the resistivity is given by rho T is equal to rho 0 into 1 plus alpha T minus T0. So this rho T, this is the resistivity of the material which we have to find at a particular temperature. For example, you want to find out 80 degree or 100 degree, what is the resistivity? That is this one. This is the resistivity at a reference temperature. For example, you know the resistivity of the material at a 0 degree or 20 degree, the particular value where we know the resistivity, that is the one. And that temperature is this one. That is, if you know the resistivity at 20 degree, this is the resistivity at 20 degree, and that 20 degree you have to write here. So when you are doing numerical problems, you can take this one in degree Celsius itself. If you are not taking in Kelvin also, it will not make any difference, because we are taking the temperature difference here. So when you take difference in Kelvin scale or in temperature, the Celsius scale, both will be same. So this is the temperature at which we know, or the reference temperature. This is the temperature at which we have to find the resistivity. And this alpha, this is the most important thing. This is called as temperature coefficient of resistivity. Okay. And it will be, the dimension of this one will be temperature raised to -1, that is per Kelvin, like that we will get this one. So this is the important equation. So whether this resistivity will increase or decrease when the temperature changes, that depends on the sign of this alpha. So if you take alpha positive value, then the resistivity will be definitely increasing. So for metals, we have positive value, and for semiconductors and insulators, no need of considering, because it's very negligible conductivity. So for semiconductors, this will be negative. So why it is happening, that we will discuss. Before that one, we will go to the graph of all these things separately. So how will be the graph looks for different situation. Now if you see the graph for a good conductor like copper, the shape of the graph is like this. So if this is, here we have the temperature and here we have resistivity. So this temperature, the scale is something like 50 degree, 100 degree, 150 degree. That range if you take, you can see the resistivity increases with the temperature. So this variation is very small. Okay, so this is in the range of 10 to the power minus 8 ohm meter, like that is the resistivity scale. So here still here it will be 0.2, 0.4. That is, we have changed the resistivity here. It is little bit noticeable change is there when you change the temperature by 10 degree, 20 degree itself, you can identify that one. So the point is our resistivity increases for some elements like copper. So this is for copper. So almost similar graph you will get for all the other conductors also. Now if you take the same thing for alloys, see here in the case of alloy, the graph is like this, your textbook graph is like this. So now you see here, the if comparing with this one, the variation is less, and again this side scale also, this is 200, 400, 600 like that. So you see here for 150 this much change is there, here this much temperature changes, that time only a small variation is there. So this is resistivity along this axis. So the difference is, if you take alloys, the alpha value is very small. So that is a very important point. So generally question used to come, why alloys are used for making standard resistors. So when we make a standard resistor, when temperature changes, the value should not vary that much. That's why if you want a standard resistance which is having very less difference when the temperature changes, then we have to go for a alloy. So the generally used alloys are nichrome, we are using as a resistor, constantan, manganese, like that many alloys are there. So all these alloys are used for making standard resistors. So we discussed about the copper and we discussed about alloys also. This is this diagram which is given is in the your book is for nichrome, which is an alloy. Now if you take the semiconductor materials, for a semiconductor material, the graph is just in the opposite shape. That is, here temperature comes, here resistivity comes, means it is going down like this. So the resistivity reduces, it becomes a good conductor when the temperature increases. Now we have to discuss why it is happening like this. Okay, so if you take the equation for this resistivity in terms of this number of electrons and all these graphs can be explained from that one itself. The resistivity is given by rho is equal to, which is 1 by sigma. This is the conductivity. So this can be written as m by n E square tau. I am writing this one like this because already previously somewhere we done sigma is equal to n E square tau by m, like that. So resistivity will be just opposite of that one. That's why this equation is written. Now you see here, if temperature changes also, this mass of the electron that won't change, charge of the electron also won't change. The possible change is the number of electrons can change. Now there is number of free electrons available for conduction, that can change. Similarly, this tau is the time interval between two collisions. Now if we go to the case of these metals, what happens is, in metal we have sufficient number of electrons. How much electrons are required, that many electrons are already available there. Now when you increase the temperature, what happens is, more and more electron will become free. But that electron will not contribute towards your conduction. Instead of that one, it will make more and more collision. When collision becomes more, what will happen? The time between two collision will reduce. So this value will reduce. Once this value reduces, the resistivity increases. So that's why in the case of conductors like copper, the resistivity increases. Now if we explain the same thing for this one, that is for our semiconductor. Semiconductor is conducting less than the conductor because of the number of free electrons available is less. Now when the temperature increases, more and more electrons will become free. So this n number will increase. So due to the increase in the number of free electrons available for conduction, the resistivity reduces. Resistivity reduces means conductivity increases. So that is the difference between a semiconductor and a conductor. So the resistivity of the conductor increases when temperature increases, and for our semiconductor it reduces. Now one more thing, previously we discussed this equation, which is the equation for the resistivity based on the temperature. Now if you are getting a problem where you have to calculate the resistance of a particular material, there simply if you replace this resistivity with resistance, same equation itself you can use for numerical problem and all.